So what is gas chromatography? Gas chromatography is the process of separation of a mixture into its components by using gas as a mobile phase that passes through an absorption layer. Gas chromatography is an analytical technique used in organic chemistry for the separation and analysis. It is applicable to gas, liquid, and solid samples, or components that are vaporized by heat. If a mixture of compounds is analyzed using the GC system or gas chromatography system, each compound can be separated and quantified. Michael Sweat invented chromatography in 1901 during his research on plant pigments. He used the technique to separate various plant pigments such as chlorophylls, xanthophylls, and charophyll. Terminologies and definition of gas chromatography. So, gas chromatography is a method for separation. Next is chromatograph. It is an instrument that is used for chromatography. Next is chromatogram. It is a data of chromatography. The advantages of using gas chromatography. First is it requires only very small samples with little preparation. It is also good at separating complex mixtures into components. And the results are rapidly obtained and has a very high precision. And on the instrument with the sensitivity to detect volatile organic mixtures of low concentrations. And the instrument or equipment that is used is not very complex, which is great. Gas chromatography is a widely used technique across most industries, including for pharmaceutical in analyzing residual solvent analysis. We also have the food and beverages in component analysis, food safety analysis, and halal analysis of alcohol. We also have the environmental in analyzing the air, water, and soil, and the petrochemicals in the analysis of simulated distillation and component analysis. We also have the industry of chemicals in analyzing the material, polymer, additive, gas purity analysis, and the gas emissions in automotives. We also have the energy and gas for artificial photosynthesis research. Here we have a diagram of gas chromatography. We have the gas carrier as the mobile phase, the sample needed in the analysis, the injector port to deliver sample to a column, and we have the column where separations occur, and the oven as a thermostat for the column. We also have the detector to register the presence of a compound in the column, and the data processor or computer to record and display the chromatogram. How does the gas chromatography works? The gas chromatography uses a carrier gas in the separation. This plays the part of the mobile phase. The carrier gas transports the sample molecules through the GC system, ideally without reacting with the sample or damaging the instrument components. So now we are going to discuss the step-by-step process of the gas chromatography. We have the step 1, the sample injection and vaporization. So in this step, a small amount of liquid sample is first introduced into the gas chromatograph to be analyzed, is drawn up into either with a syringe or transferred from an autosampler that may also extract the chemical components from solid or liquid sample. Then, the syringe needle is positioned in the injection port of the gas chromatograph, and the sample is injected quickly through a septum, which enables the injection of the sample mixture without losing the mobile phase. Moving on to the step 2, the separation in the column. So there are two main types of separation column used in the gas chromatography available on the market. We have the capillary and packed columns. Note that the carrier gas is inert and does not interact with the sample, and thus the gas chromatography separations selectively can be attributed to this stationary phase alone or in the column. However, the choice of carrier gas is very important to maintain high efficiency. The effect of different carrier gases on the column efficiency is represented by the Van Demter or packed columns and the Golay equation or capillary columns. So, in step 2, in the process, the sample moves through the column through the flow of inert gas. The analytical column is held in the column oven, which is heated during the analysis to elute the less volatile components. The columns are mounted in an oven with precise temperature and carrier gas flow control. And the higher the column temperature, the faster the sample moves through the column. Moving on to the step 3, the last process, the detecting and the recording of results. So once the separated gases leave or elute from the column, the outlet of the column is inserted into the detector, which responds to the chemical components eluting from the column to produce a signal. Then, the signal is recorded by the acquisition software or on a computer to produce a chromatogram.
Laboratory equipment or apparatus involved in gas chromatography. We have carrier gas. Example of these are argon and helium. We have also gas chromatography machine. We have also flow regulators, which is composed of two. These are rotameter and soup bubble flow rate. We have also injection devices, which is also composed of two. We have also micro syringe and gas-tight syringe. We have pack column, we have capillary column, and last but not the least, detectors. Reagents involved during the process of gas chromatography. There are four types. These are acylation reagents. It converts compounds that contain active hydrogens through the action of a carboxylic acid or a carboxylic acid derivative. Acylation reagents. It is the most widely used derivatives for gas chromatography application. Alkylation reagents. It is the substitution of an active hydrogen by an aliphatic or aromatic benzyl group or modifying compounds containing acidic hydrogens such as carboxylic acids and phenols. Last but not the least, siliconizing fluids. It coats various lab consumables with an inert water repellent film. Measurements that are needed in the process of gas chromatography. As we can see, we have a chromatogram. It says that the x-axis is the retention time. taken from the time the sample was injected into the GC to the end of the GC run. Each analyte peak has a retention time measured from the apex of the peak. For example, PR. The y-axis is the measured response of the analyte peak in the detector. Narrower, sharper peaks give better sensitivity, which is signal-to-noise ratio, and better resolution, which is peak separation. The peaks shown are Gaussian. However, peak-tailing the right side of the peak is wider indicates the activity or a dead volume in the system, whereas a peak fronting the left side of the peak is wider indicates the column is overloaded. Accurate measurements are affected by the number of data points across a peak, with an ideal number of 15 to 25. Too few makes the peak look like a child's join the dots drawing, affecting peak area, resolution, and with GCMS deconvolution. Too many reduce the signal to noise, reducing sensitivity for GCMS data. Each data point is a mass spectrum, the third dimension of data. The baseline shows the signal from the detector when no analyte is eluting from the column, or it is below the detection limit. The baseline response is a mix of electrical noise, usually low, and chemical noise, such as impurities in the carrier gas, column stationary phase, bleed, and system contamination. Hence, the baseline is higher than it should be. It is an indication of a problem that maintenance is required. Various measurements can be taken from the peak, such as width at the baseline, width at half height, total height, and area. The latter two are proportional to the concentration. However, it is the area that is used for quantitation, as it is less affected by band broadening. The measurements can be used to calculate the extent of band broadening, the spread of the analyte molecules, and the column.